This is the Module 2A video on the epoxidation of alkenes. Once again, I will use 1-methyl-cyclohexene as the test substrate. Many peroxycarboxylic acids will promote this reaction, but one of the most common is metachloroperoxybenzoic acid, often known by the abbreviation MCPBA. The bicarbonate base is optional for these reactions, but it does buffer the carboxylic acid that is generated as a byproduct. This particular reaction proceeds in very high yield. The reaction mechanism follows a concerted pathway, breaking the thermodynamically weak oxygen-oxygen bond with an oxygen forming bonds to the adjacent carbons coming from the alkene, also producing carboxylic acid as a byproduct. In the class meeting, we'll discuss the reasons why only one oxygen adds to the alkene. Scrolling down the page, epoxides are often formed as stable synthetic intermediates, but because of the ring strain of the three-membered ring, epoxides are generally much more reactive than other ethers. However, the epoxide dissolved in methanol solvent does not react even after prolonged heating at or above the reflux point of methanol. It's only when acidic or basic co-reactants are present that a reaction will occur. In the presence of sulfuric acid, the epoxide opens in the presence of methanol at 20 degrees Celsius to give primarily the methyl ether with carbon-oxygen bond forming at the more substituted carbon 1, with the hydroxyl group coming from the epoxide oxygen. On the other hand, the basic reagent, sodium methoxide, although it reacts more slowly and requires higher temperature to get a reasonable rate, methoxide adds virtually exclusively at the less substituted carbon, carbon 2. And now the hydroxyl group that comes from the epoxide oxygen is attached to carbon 1. On the last page of the worksheet, I'll describe mechanistic proposals for methanol addition. Under acidic conditions, sulfuric acid predominantly protonates methanol, and then there's a proton transfer in equilibrium between protonated methanol and the epoxide oxygen. This puts a positive charge on the epoxide oxygen, making it much more electrophilic, undoubtedly lowering the energy of the LUMO, and attracting methanol, which is a weak nucleophile, but it reacts at the more substituted position, analogous to what happens with reaction of the bromonium ion with a nucleophile. And then proton transfer from the methyl ether to methanol allows for the acid catalyst to be regenerated and gives the hydroxy ether product. Under basic conditions, the epoxide can react with methoxide anion at either one of the carbons of the epoxide. But the reaction rate is faster at the less sterically hindered carbon. This reaction resembles the mechanism for bimolecular substitution, so that the major product is the secondary ether, and after protonation from solvent, the tertiary alcohol. In the video, I think I have now described why methanol selectively adds to C1 under acidic conditions and at C2 under basic conditions. But I hope to save some time at the end of the class period for this discussion in case you have some questions over these two mechanisms. This concludes the Module 2A video on the epoxidation of alkenes.